Okay. Yeah, so this is the model that we were looking at last time. So dRdt is the changes in Romeo's feeling over time, and then dJdt is the change in the Juliet's feeling towards Romeo over time. Right, so we get two parameters here. The A that measure the consciousness of the self feeling towards the other person. So we have A times R, and then B times J. So B here is the measure of responsiveness of the other person's feelings towards this person. So Romeo's responsiveness towards Juliet's feeling. Okay, so here because A is a measure of consciousness, A is negative, right? Because if you're self-cautious, that means your feelings towards the other person will decrease over time. And then B is positive. And here we have another restriction that the absolute value of A is not equal to B. Okay. So we work it out and we find the general solution to the system, right? Using the eigenvalues and eigenvectors. So when you have the coefficient matrix like this, you can find the eigenvalues. And for this example here, the eigenvalues are A plus B and A minus B. And the associated eigenvectors are 1, 1. That's the eigenvector associated with A plus B. And 1, negative 1, that's the eigenvector associated with the second eigenvalue, A minus B. Okay, so then when you write down the general solution, this is how it looks like. All right, so now we want to look at the second one is you want to look at the fixed point and then look at the phase portrait, because phase portrait can tell you the behavior in the long run. So that means you can do some forecasting of what happens to this pair. Okay. All right, so one restriction that we have for the parameters is that absolute value of A is not equal to B. Okay, so therefore we have two cases. The first case is when it is greater than B, and then the other one when the absolute value of A is strictly less than B, right? So not equal means either greater than or less than, okay? So I think we were running out of time, so we end up only with case one. That's the one that we were kind of trying to figure out. Okay, so here, remember A is a negative parameter, right? And then B is positive. And we want to look at, given this restriction on A and B, how is lambda 1 and lambda 2? Are they positive or are they negative? Because they affect the stability of the fixed point. Right, so just take, for example, A is negative 5 and B is 2. Right, so here, obviously, A is negative, B is positive. And if you take the absolute value of A, you get 5, and that's greater than 2. Right, so just using this A and B, we can see that when you have A plus B, then this lambda 1 is negative. And then A minus B is also negative. So both lambdas are negative. That means your fixed point, which is the origin, is a stable equilibrium or stable fixed point. And because they are both real numbers, we don't have spiral, but we have what we call the sink. And then the other thing that will help us in sketching the phase portrait is the eigenvector. So we know that eigenvector phi1 and phi2, we already found it. So phi1 is 1, 1, and phi2 is 1, negative 1. So when you sketch the span of those eigenvectors, you get these two lines, right? So phi1 associated with lambda 1 and phi2 associated with lambda 2. Because both of them are negative, that means the straight line solution, the flow pointing towards the origin. Okay, so therefore we have these arrows. Now, what about the other trajectories? Also notice that comparing lambda 1 and lambda 2, okay, so just use this value, A is minus 5, B is 2. Lambda 1 will be negative 3. And lambda 2 is minus 7. So lambda 1 is greater than lambda 2. Now, what does that tell you? So if lambda 1 is greater than lambda 2, that means in the long run, as t goes to infinity, your trajectory is going to be parallel to phi1, right? The eigenvector associated with the bigger lambda. Okay, so that means when you sketch the other trajectories, is going to look, well, maybe initially it's parallel to phi2, but then as t goes to infinity, it's going to be parallel to phi1. Okay, so you have something that looks like that. Okay, so depending on where is your initial point, basically your other trajectory looks something like this. Okay, so oops, this one doesn't really look good. Initially you might be parallel to phi2, but then as t goes to infinity, it's becoming parallel to phi1. But all of them are getting closer and closer to the origin. All right, so any questions on case 1?
I have a question.
Uh-huh.
In the context of the Romeo and Juliet, what does this mean?
Yeah, what does this tell you? Okay, so, well, you have some initial conditions, right? Maybe you can think, well, okay, how is their initial feelings? Maybe both of them start to like each other initially, right? So that means your initial point may be somewhere on the first quadrant, maybe somewhere over here. Okay, this is your initial point. And then look at the trajectory that passed through that point. Remember, by existence and uniqueness theorem from differential equation, there is a unique trajectory that passed through that point. So if you follow the trajectory, it's going to point towards the origin. Okay, so initially you start here, and as time goes on, where do you end up? You end up at the origin. What does that mean? That means R is 0 and J is 0. So that means nothing will happen. At the end, their feelings towards each other become 0. Okay. Or if you start with a different initial points, for example, maybe you start with a point over here, right? Yeah, so by the way, let's label the axis. So we use, okay, R. So R will be the horizontal axis, and then J is the vertical axis. So if you start with the point over here, so that means R is positive and J is negative, right? So that means Romeo likes Juliet and Juliet dislikes Romeo initially. And then you look at the trajectory that passed through that point. And then, well, this is how it looks like. Yeah, maybe initially it's parallel to phi2, but then still you end up at the origin. That means at the end, they both have no feelings towards each other. Okay. Yeah, so you can interpret this by saying that all solution converge to 0, 0. So nothing will happen. Regardless. How much they like or dislike. Initially.
Love you.
All right, so any questions on this?
Sorry about that. I appreciate you. Have a great day. Gotta go.
Did I answer your questions, Edgar?
Yes.
Yeah, okay. All right, yeah, so that's what happens when your cautiousness is greater than your responsiveness. Okay, so which kind of makes sense if you look at the parameter value, right? A, measure cautiousness, and then B, measure responsiveness. If you're more cautious, yeah, of course, nothing will happen. Okay. All right, now let's look at case 2. Okay, so for case 2, absolute value of A is strictly less than B. Okay. So how is this lambda 1 and lambda 2? Okay, let me do it. All right, so lambda 1 is A plus B, and lambda 2 is A minus B. Again, remember here, A is still negative, and B is positive, but then absolute value of A is less than B. So you can maybe just pick an example, make it easier to see. Pick A to be -2, for example, and then B maybe 5. Okay. Okay, absolute value of A is 2, so that's still less than B. All right, so now how is A plus B? So that will be 3, that's positive. And then A minus B is -7, so that's still negative. Okay, so what can we say about this fixed point? Stable, unstable, saddle, spiral? What do you think? Anyone? So it's a saddle, right? When one is positive, the other one negative, you get a saddle. All right, so now let's sketch the face portrait. Okay, so this is R axis, that's the J axis. We still have V1 and V2. Let's see, V1 is 1, 1. Okay, so you get something like this. This is span of V1. V1 is the eigenvector associated with lambda 1, but lambda 1 is positive. So that means the flow is going away from the origin. So that means you're going outward like this for V1. And then V2, yeah, the other eigenvector is 1, -1. So it will be something like this. Oops. Okay, so that's your V2. And the eigenvalue associated with V2 is negative. Lambda 2 is negative here. So that means the flow is pointing towards the origin. All right, so you know how the saddle looks like. So we can sketch the other trajectories. Basically, you can start from somewhere over here, right? And then following V2. And as you get closer to the origin, your V1 is going to take it away from the origin. So it's gonna look like something like this, okay? All right. Now, what is the interpretation of this? Anyone want to give a guess? What do you think? So just take, for example, pick a point, maybe somewhere over here, right? So that means what? The R is negative, but the J is positive. So Romeo initially dislikes Juliet, but then Juliet likes Romeo initially. And then look at the trajectory that passed through that point, okay? So trajectory that passed through that point is still looks something like this, okay? So initially you're kind of like going towards the origin, but then, you know, V1 is going to take it away from the origin. And what happens in the long run? What happens over here? So Juliet becomes positive and R is also positive. So that means they both like each other, okay? Now let's pick some other initial point. Say if you pick, well, maybe somewhere here, maybe we can even start with the same quadrant. Here Romeo is negative, so initially dislike Juliet, and then Juliet likes you, Romeo, because it's positive above the r-axis, and then follow the trajectory. Okay, obviously these two initial points are different, so they might start with different, likeness or dislikeness towards each other. Okay, if you can quantify that, and then follow the trajectory is going to end up something like this, right? Now what happens here? So it looks like you're going towards the third quadrant, meaning that J is negative and R is negative. So that means they both end up disliking each other. Okay. So looking at this, look at what happens, look at the arrow. So either they are going towards quadrant 1, go all the way up, or quadrant 3, go all the way down. So that means they both end up liking each other, or they both end up disliking each other. Okay, so in this case, the feelings are eventually mutual, right? They both like or they both dislike each other. Yeah, so for this one, the interpretation is that all trajectories are approaching the line. So this horizontal line, the line J equals R. Okay, really that V1. Okay, so the feelings are eventually mutual. Okay, so either both like or dislike each other. Okay. All right, any questions here? If you have questions, feel free to put it in the chat. Yeah, so Jeremy is also right. Either they love each other or they hate each other. Yeah, so this is only mathematical analysis. So yeah, just a disclaimer. I'm not responsible if you try to apply it on your personal life. Okay. All right.
Results
What
may vary.
happened? Yeah, there's a question here in the chat. What happens when initial values are within the vectors? Yeah, so here you mean like along V1 or along V2? So if they are along V1, right? So just say you have initial value here, then you follow the arrow, they both like each other. Or if they start with the initial value right there in the quadrant 3, so they dislike each other, then they will dislike each other forever. Okay. Or if they start with somewhere here, then yeah, one like and the other dislike. So at the end, let's see, where did it go? So you're not going to point towards the origin in that case. So here, let's see. That's a good question. So what happens right there? Anyone have an idea? What do you guys think? Look at the trajectory that passed through that point. If you start here along V2, then you following the arrow, you go to the origin. And that's the only way you could go to the origin. But then if you're just a little outside V2, then yeah, you don't end up at the origin. You go following V1 here. Okay. So yeah, only very specific initial point would end up at the origin, which is the one along V2 and nothing else. All right, any questions about this model? Oh, no questions? All right, so if no questions, I think I want to start with the nonlinear. Yeah, so let's look at the nonlinear ODE. So I'm going to start with the ideas first. What is the steady state? How do you look at stability? And then after we're done with this handout, then we're going to start look at the application. So after this handout, everything just application. Okay, so we're going to look at the compartmental model again, mixing problems, and then we'll look at predator-prey. And after that, I want to look at the SIR model. We're going to go back to that, and the combat model. Okay. And I think that will be it. We don't have that much time until your second test. All right, so now let's look at the nonlinear autonomous ODEs. So you're gonna deal with more than one ODEs this time. And then if you look at the right-hand side, F1, F2, all the way to Fn, they are not necessarily linear. Okay. So here, if you write it as a vector notation, we get dx dt, which represent the vector of the first derivative, dx1 dt, dx2 dt, all the way to dxn dt. And then the vector f on the right-hand side is the vector consisting of pretty much the right-hand side of your ODE. Okay, could be nonlinear equation. F1 to Fn could be nonlinear. Now, the steady state or fixed point or equilibrium is the same idea as in the linear case, basically when the derivative is equal to 0. Okay, so what you do to find the equilibrium here is you set each of these F1, F2, all the way to Fn equal to 0, and then solve for x1 through xn. All right, so here, let's just do the system of two ODEs.
Can you move up a little bit? There we go. Just a little downward, please. Just go to where? Okay. Okay, that probably should be good.
Yeah, so here the steady state, basically the definition is the same as in the linear case, right? So you set each derivative equal to 0 and then solve for x1 through xn. Okay. Now for the nonlinear case, you might have more than one fixed points. Okay, so unlike the linear case, most of the time you just have the origin 0, 0. But then here for the nonlinear, you might have more than one equilibria or more than one fixed points. Okay. Okay, can I scroll down now? All right, so now let's look at the system of two ODEs, dx dt and dy dt. Right-hand side is f and g. So here I denote the steady state as x star, y star. Or if you don't like this, then you can drop the asterisk. So here f of x star, y star is 0, and then g of x star, y star is also 0. Okay, so now let's do stability analysis. Sometimes it's called linearization because it's not easy to find the solution for the nonlinear system. But if we linearize it near the fixed point, then you get a linear system, and then you can find the approximate solution. And then from there, you can analyze the stability of the fixed point. Okay, so we try to linearize this nonlinear system and then use the technique that we did for the linear ODE, linear system, to analyze the stability. Okay. All right, so again, stability means that if you apply a small perturbation away from the equilibrium, then this perturbation is going to get smaller and smaller, or is going to decay, and your solution is going to go back to x star, y star, your fixed point. right? Now, I'm going to let u be equal to x minus x star, and v is y minus y star. Okay, so these two gives you the amount of the perturbation away from the fixed point, x star, y star, right? And you can assume that they are relatively small. Okay, so now let's take derivative with respect to t. Okay, so the first one is this one, u equals x minus x star. Okay, so both of them are functions of t. Okay, so when you take derivative with respect to t, du dt is dx dt minus dx star dt. Okay, when you take derivative, you take derivative term by term. Dx star dt, we know this one is equal to 0. And that's because x star is constant. That's the x coordinate of your fixed point. Right, so then derivative of a constant is 0. All right, so that leaves us with only dx dt. But then dx dt is f of xy. Okay, so that's the right hand side of your first ODE. All right, and then x, well, if you solve for x from this equation, x is u plus x star. All right, so then I'm gonna write x as u plus x star or x star plus u. And then likewise for y, so if you look at the second equation here, you can write y as y star plus v. Okay. And then now I want to do a Taylor series expansion. Okay, so this is a Taylor series for functions of two variables, right? So Taylor series expansion for functions of two variables, x and y. So here, so you would expand around x star, y star, around the fixed point. So we have f of x star, y star plus u. So we look at the amount of perturbation along the x direction. So it'll be u times the derivative with respect to x. But then since this is functions of two variables, you don't put df dx, but then you put partial derivative. Yeah, when you have functions of more than one variable, when you take derivative, it will be partial derivative. So here we'll take partial with f with respect to x, evaluate it at the center of this Taylor series, which is x star, y star. And then look at the perturbation along the y direction. So you get v times partial derivative with respect to y. Again, evaluate this at the center. And then now going into the second derivative, you get u squared over 2 factorial times the second order partial derivative. Again, evaluate at the center. And you get v squared over 2 factorial partial derivative with respect to y. And we also have the mixed partial, right? So you get u v times the mixed partial derivative with respect to x and y. Again, evaluate at the center. Okay, and then you have a lot more terms for the higher order partial derivatives. But this is enough because again, we assume that u and v are small. So if u and v are small, when you square it, u square and v square even smaller, right? So here, if you just want to do approximation, you can ignore this part, and everything of higher order derivative, because you're gonna have u squared, u cubed, and higher exponent. Same thing with the phi. Okay, so here we can say this quantity are small as u and phi are also small. Okay, so that means your du dt can be approximated just by these three terms over here. And even more, we know something about the first one. How much is f evaluated at x star, y star? How much is this quantity? So this one is 0, right? Because x star, y star is a fixed point. And the way you find fixed point is by setting f and g both equal to 0. So the first one is 0. So really, the approximation to du dt is just u times partial of f with respect to x plus phi times partial of f with respect to y. Okay, so notice I use the squiggle sign instead of equals because this is just an approximation. Okay. All right. So now we're gonna look at dphi dt, and then the work is pretty much similar to the one I just showed you, but this time you take partial of phi with respect to t, and then you use this equation, the phi equals y minus y star. Okay, everything else the same. dy star dt, that's equal to 0 because y star is constant. Okay, and then again, we use the Taylor series expansion, apply to G, and then evaluate at the center x star, y star. Okay, and then at the end, we have an approximation to dphi dt. So we just have u times partial of g with respect to x plus phi times partial of g with respect to y. Okay. Yeah, so now let's look at these two equations. This is equation 1. Okay, so I'm just taking this one over here and also this equation 2. Okay, so I want to combine these two. And you can see that we multiply this partial of f with respect to x with u, and then we multiply partial of f with respect to y with phi. Okay, and these partial derivatives is actually just constant because you evaluate them at x star, y star at the fixed point, right? So here, the coefficients of u and phi on the right-hand side are just constant. So if you put them in the matrix, okay, so put du dt and dphi dt as a factor of the first derivative. So we have left-hand side, you just get du dt and dphi dt. And then on the right-hand side, you have the matrix of partial derivatives evaluated at x star, y star, multiply with the factor u v, right? Just like in the linear system, right? You can put it in the matrix form, and then you just have a linear system like this. Okay. This matrix, I call it matrix A, is really the Jacobian matrix evaluated at the fixed point x star and y star. Okay, so this is the linearized system near the fixed point. Okay. So from here, we can get an approximation to the nonlinear system that we have initially. And then we can also use the stability analysis that we did before to analyze the stability of the fixed point of the nonlinear system. Okay, so stability analysis can be done as in the case of linear system. So here, what I mean by that is that check the eigenvalues of A to determine the stability. Okay, so right now the system that we deal with is just this, right? Linear. Yeah, so as an example here, remember in the linear system, your fixed point is 0, 0. And say that one turns out to be a stable equilibrium. That means that u phi approaches 0, 0 as t goes to infinity. And because u is defined to be x minus x star and phi is y minus y star, so if both u and phi approaches 0, that means x will approach x star and then y will approach y star. So that means your solution x comma y will approach the fixed point x star y star in the long run. Okay, so yeah, basically you can go back to the stability analysis for the linear system. All right, any questions here before we look at examples? Oh, no questions? All right, so if no questions, let's look at the first example here. Okay, so you have nonlinear system, dx dt is minus x plus x cubed, and dy dt is minus 2y. Find all the fixed points, classify them. Is it a sink, is it a saddle, or is it a spiral? And then sketch the phase portrait. Okay, so the phase portrait that you sketch will contain all the fixed points, all the eigenvectors, and also the trajectories. All right, so start with the fixed point. So how do you find the fixed points? Okay, so for the fixed point, you will set both x star equals 0 and, no, not x star, I mean dx dt, the derivative equal to 0, and derivative of y also equals 0. All right, so you can choose which one you want to work on first. So say if I pick the first one, then I get minus x plus x cubed equals 0. You can factor out the x. And you get x times minus 1 plus x squared equals 0. So we have x equals 0. And then here you can have 1 or negative 1. So you get 3 possible x values. All right, so now let's look at the other one. dy dt equals 0. But then dy dt is just minus 2y. So minus 2y equal to 0, that means y is 0. Okay, so you get the x value, but then the y value is always 0. So combining this, you get fixed points. Well, actually, you get 3 of them. The first one is 0, 0. And then you have 1, 0. And then you have minus 1, 0. Okay, so you get 3 fixed points. All right, now what about the stability? So for stability, let's look at the Jacobian matrix. Okay, so construct the matrix A, which is the matrix of the first partial derivatives. So the first row will be partial derivative of f with respect to x, partial of f with respect to y, and then the second row, partial of g with respect to x, and partial of g with respect to y. Okay, so that's a 2 by 2 matrix. Okay, so what is f and g? So f and g are just the right-hand side of your ODE. So this is f here, and that is g. Okay, so the first one I need partial of f with respect to x. So how much is that one?
3x squared minus 1.
3x squared minus 1. Yep. All right, so what about partial of f with respect to y? Okay, so if you look at f, there is no y in here, right? So partial with respect to y will be 0. Yeah. All right, second row, partial of g with respect to x. That is g. G is minus 2y.
0.
0. And then partial of g with respect to y.
2. Negative 2.
Negative 2. Yep. Okay, so your Jacobian matrix may have some variables in it, but then to analyze the stability, you will plug in the fixed point. So we got 3 fixed points. That means you gotta evaluate A at 3 different fixed points. Okay, so let's look at the first fixed point, which is 0, 0. Okay, so that means x and y values are 0. Now here, when you plug in 0 for this x, we get minus 1, 0, 0, negative 2. Right, you get that matrix. Okay. And now we need to look at the eigenvalues. Just like in the linear system, when you have the coefficient matrix, you look at the eigenvalues, right? So what's the eigenvalue for matrix A here?
2.
So there are 2 eigenvalues because this is a 2 by 2 matrix. So what are they? Can you see it quickly?
-1, -2.
-1, -2. Okay, you can take advantage that your matrix A here is a diagonal matrix. In fact, for triangular, either upper triangular or lower triangular, the eigenvalues, you can just read the main diagonal entries, right? So here, this is a diagonal matrix. So that means eigenvalues are the main diagonal entries. Well, of course, you can always use this characteristic polynomial and then solve for lambdas, but this one is a lot faster, right? So lambda 1 is -1 and lambda 2 is -2. Okay, so just read the main diagonal entries. And also the fact that this is diagonal matrix, your eigenvectors is also easy to see. The associated eigenvectors for lambda 1, look at lambda 1 is -1, which is the entry in the first row, first column. Then the associated eigenvectors is going to be 1, 0. And then lambda 2 in the bottom corner. So the associated eigenvector v2 is 0, 1. Okay, so you can take like a shortcut from linear algebra just to minimize your work. All right, so that's your lambda 1, lambda 2. Both of them are negative. That means, what can we say about your fixed point?
Stable.
Stable. And this one are real, so that means we have a stable sink. Okay. All right, let's move on to the next fixed point. Your next fixed point is 1, 0. Okay, so now x value is 1, y value is 0. Now your matrix A is this. So if x is 1, so the first entry would be 2. And then everything else are constant, 0, 0, -2. All right, so again, we end up with the diagonal matrix, which is nice. So here, lambda 1 is 2, lambda 2 is -2. So that means, what can you say about this fixed point?
A saddle.
It's a saddle. Okay. Again, we will need eigenvectors when we sketch the phase portrait. So V1, your eigenvector will be 1, 0, and V2 will be 0, 1. Okay, look at the last one. Your third fixed point, -1, 0. Okay, so when x is -1, let's see. So when x is -1, we still have 2 in the first entry here. Everything else the same, 0, 0, -2. Okay, so this is the same as the previous fixed point. Okay, because lambda 1 is positive, lambda 2 is negative. Therefore, -1, 0 is also a saddle. And then V1, 1, 0, and V2 is 0, 1. All right, so now we want to combine all of these 3 fixed points and then sketch the phase portrait. All right, let's see. Okay, so this is your y-axis, x-axis. So we got 3 fixed points. The first one is the 0, 0 origin. And then you have 1, 0. And then -1, 0. Okay, so those are your 3 fixed points. Now let's sketch the straight line solution. I'll start with the first one. Okay. So at 0, 0, we have 2 eigenvectors, 1, 0, and 0, 1. Okay, so 1, 0 is just basically the x-axis. And V2, 0, 1 is the y-axis. Okay, so here, along the x-axis, you have your V1. And then along the y-axis, that's your V2. All right, so for the first one, both lambdas are negative and 0, 0 is stable. So that means the flow are pointing towards the origin. Okay, so that's the first one. Now the second one at 1, 0. So your V1 and V2 are the same, 1, 0 and 0, 1. So if you sketch V1, which is 1, 0, from the point 1, 0, we still get pretty much the x-axis, right? We sketch the span of V1. But then when you sketch the span of V2 from the point 1, 0, then we will have this line over here. Oops, I missed that. Okay. So that's your V2 for the second fixed point. But then you look at the lambdas. Okay, so lambda 1 is 2. So that means along V1, the flow is moving away from 1, 0. Okay, so here along phi1. So you already see that from the previous arrow that we drew, it's moving away from 1, 0. So that means here it's also moving away. Now along phi2, lambda 2 is negative, so that means the flow is moving towards 1, 0. So you get this arrow over here. Okay. Now at minus 1, 0. So again, phi1 is 1, 0. So the span of phi1, we still get the x-axis. And then the span of phi2, we will have this vertical line right here. Okay, so this is the phi2 for the third fixed point. Now look at the lambdas. Lambda 1 is positive, lambda 1 is 2, so that means along phi1, the flow is moving away from minus 1, 0. But then along phi2, because lambda 2 is negative, the flow is pointing towards minus 1, 0. Okay, so this is the straight line solutions with the arrows, with the direction. Now we know that minus 1, 0 and 1, 0 are saddles. So how do we sketch the remaining trajectories? Well, here I'm gonna sketch a few of them. So here, say if I start from the point over here, then we're going to follow phi2, parallel to phi2, and then going towards the origin. Or if you start somewhere over here, then we're going down, following phi2, and then this green arrow is going to bring this trajectory towards the origin as well. Okay. So if you start down here, the flow is going like this. And if you start here, again, you're going to go towards the origin. But then if you start over here, it's not going to go towards the origin, because to go towards the origin, you have to cross phi2, and trajectory cannot cross. So here, because 1, 0 is a saddle, you're going to have something that looks like that. Okay. So basically, none of this trajectory can intersect each other. So you have something like this on this side, and same thing over here. You're gonna have something that looks like that. Okay. Yeah, so this is the phase portrait for this nonlinear system. Yeah, so this is your fixed point here, and also this one. Okay. All right, any questions on this example? If you have questions, feel free to type it in the chat. Too complicated. Yeah, math is complicated. No one say math is an easy major. All right. So if no questions, let's try number 2. Yeah, so for number 2, it just asks you to find all the fixed points and determine the stability. Okay, so you don't have to sketch the phase portrait for number 2. All right, so fixed point. set the derivative equal to 0. You can choose whether you want to start with dx dt or dy dt first. Looks like dy dt is probably a bit simpler, so I'm gonna take this dy dt and set it equal to 0. Okay, so I can factor out the x. So you have 1 minus xy equals 0. So we get x equals 0 here, or 1 minus xy equals 0. So xy equals 1. Okay. All right, so now we gotta use the first one. We will substitute this to dx dt, which is 2 times 2 minus x plus x squared y. Okay, so take the first one, x equals 0. Okay, so when x equal to 0, what do we have here? So we get 4. Okay, and that can never be 0. Okay, so this is a contradiction. So we don't get any fixed point from x equals 0. But then we have to do the other one also. X times y equals 1. So here, well, maybe you can solve for x and just write x equals 1 over y. Okay, so again, substitute this to dx dt. If x equals 1 over y, then we'll get 2 times 2 minus 1 over y plus x squared is 1 over y squared times y. So when you simplify, well, you want to set it equal to 0. So this will be 4 minus 2 over y plus 1 over y equals 0. So we have 1 over y equals 4, and y equals 1 over 4. Okay, so y is 1 over 4, then x is 1 over y, so x will be 4. All right, so that's the only fixed point we have. Okay, so here we have the fixed point equals 4 and 1 over 4. All right. Yeah, so nonlinear system doesn't always give you more than one fixed point. Sometimes you still have one. Sometimes you can have more than one. Just like in the previous problems, we end up with 3 fixed points. But then this one here, even though the system looks a bit more complicated, but we only have one fixed point. Okay, so you just have to compute this carefully and then see what you have. All right. Now how do you look at the stability?
Through the Jacobian.
Yeah, look at the Jacobian. Okay, so I'm gonna, yeah, let's copy this problem so we don't have to scroll back and forth. I'll put it here. All right, so let's look at the Jacobian. This is partial of f with respect to x. partial of f with respect to y, partial of g with respect to x, and partial of g with respect to y. Right, so this is your f, and this is your g. All right, what is partial of f with respect to x? So remember from calculus that if you take partial derivative with respect to x, you treat x as your variable, and then y is just a constant, right? So if you look at f, well, here, if you want to distribute the 2, you'll get 4 minus 2x plus x squared y. So partial of f with respect to x, so x is your variable here. What would that be?
-2 plus 2xy.
Yeah. Minus 2 plus 2xy. Okay. Y is just a constant here. Now, what about partial of f with respect to y? So treat x as constant.
X
So,
squared.
yeah, okay, it's just x squared. Okay, so now look at g. What is partial of g with respect to x?
One minus 2xy.
1 minus 2xy. And then partial of g with respect to y?
-x squared.
All right. All right, so great. So now evaluate this at the fixed point at 4 and 1/4. So let's see, what do we get? We get minus 2 plus 2 times 4 times 1/4. And we get 4 squared minus 2, 1 minus 2 times 4, 1/4, and then minus 4 squared. All right, so we got 0, 16, minus 1, and minus 16. All right, so this is your matrix A. Unfortunately, there is no special structure of matrix A. This is not a lower triangular, by the way. I know it looks like a triangle right there, the non-zero entries. Yeah, so this is not a lower triangular, so don't just read off the main diagonal entries and then say that's the eigenvalues, right? So here, you have no special structure for matrix A. Compute the eigenvalues using the characteristic polynomial. Okay, let's look at the eigenvalues. So determinant A minus lambda I, set it equal to 0. So here, A minus lambda I would be this matrix, minus lambda, 16, minus 1, minus 16 minus lambda. So determinant would be minus lambda times minus 16 minus lambda minus 16 equals 0. So you get lambda squared, 3 plus 16 lambda plus 16. Let's see, is it factorable? Doesn't seem like it. Okay, there is always quadratic formula. Right, so you get minus b plus a minus square root of b squared minus 4 ac divided by 2a. Okay, so this is minus 16 plus or minus. So that's 256 minus 64, 192 over 2. So looks like both of them are negative. Okay, let me check real quick. Yeah, so one of them is negative 1.07, and the other one is about minus 14.93. So both lambdas are negative, right? So that means what's the conclusion?
It's a sink.
Yeah, so you get 4 and 1 over 4. That's your fixed point is a sink, or it's a stable fixed point. Yeah, so if you're not asked to sketch the face portrait, then basically the analysis is just find the Jacobian, evaluate at the fixed point, and then look at the eigenvalues. Okay. All right, so we're done with the discussion of the nonlinear system. So I think after this, everything is just going to be application until we're done with all of them. Okay, any questions here?
How different do the graphs look if they were complex?
So how different the graph looks if they are complex? It's, well, for complex, you still have a spiral, right? Or if it's pure imaginary, you have a center. So yeah, think about, what we sketched before when we talk about the linear system, but kind of like put everything together on the XY plane.
Okay.
Yeah, so we'll do more examples. I will show you MATLAB when we get to some example, maybe like predator prey. That's a good one. Yeah, I will have the MATLAB code. I will show it to you and I'll also put it on Canvas, okay, in case you want to do something along that line for your final project. Yeah, and definitely there are a lot more application for the nonlinear system than linear system.
Thank you.
Any other questions for today? No? No questions? Yeah, I still have office hours in person. I'm in my office right now. So yeah, so feel free to stop by if you have any questions or if you want to talk about your final project. All right, if no more questions, that's it for today. I'll see you guys on Thursday, hopefully in class.
Bye.
Bye.
Thank you, Professor.
Thank you,
Bye.
Professor.
Thank you, Professor.
All right.
Thank you, Professor.
Okay, take care, everyone.